Okay, so now I want to talk about when a function is not differentiable. So when can a function fail to have a derivative? The first way we saw in the last video is if f of x is not continuous at a point x equals a, then it doesn't have a derivative. So let's say when is it not differentiable at x equals a? So when does the derivative not exist at a point x equals a? And in the last video, we saw that if f is not continuous, then it doesn't have a derivative. So this is the first way. And I want to talk about two other ways that a function can fail to be differentiable. So another way to say this question, to rephrase this question, is to say when does the definition of the derivative, when does the limit not exist, right? So this is when does the limit of f of a plus h minus f of a over h, when does it not exist? So when does it fail to exist? And so we can think about like how can a limit fail to exist? There are a couple ways that a limit could fail to exist, right? So if the limit has two one-sided limits that are different, right? So like if I looked at the left side limit and it approached one point, and then I looked at the right side limit and it approached another point, this is a way that the limit could fail to exist. And what does that mean for the slope? So if the derivative, the difference quotient here, is approaching one thing from the left side and another thing from the right side, what does it mean? So this difference quotient, it's measuring the slope of the line between 2 points on the function, right? So that means if I take 2 points where one is on the left-hand side, then the slope is tending to some value as I squeeze these points together. So it might look something like this. And then if I take the difference quotient on the other side, then the slope is approaching a different value. So it might look something like this, right? So what this is saying is if the two one-sided limits are different of this difference quotient, it means that from one side of the function, the slope looks like one value, and from the other side, the slope looks like a different value. So in this case, we have something that's like a corner, or sometimes this is called a cusp. So the function could look like this if it's a corner. When the function is more curved like this, it's called a cusp. And so in this case, like the derivative is not defined, right? The slope of the tangent line is not defined at this point. And it's because the two one-sided limits are different from each other. Another way that a limit can fail to exist is if the limit is infinity, right? Plus or minus infinity, right? So if the limit is plus or minus infinity, then the limit doesn't exist. And what does this mean for this, the function, the original function, right? So if the slope is approaching plus or minus infinity, it means that the tangent line to the function at that point is vertical. Okay, so if the tangent line is vertical, then the limit of this function is plus or minus infinity, and so this is another way that the limit could not exist. So if the tangent line is vertical, we say the function's not differentiable. Let me give you an example here. If f of x is the cube root of x, so x to the 1/3, you can work out what the derivative is, or you can use the power rule that we're going to learn in a few days, and understand that the derivative of this function is 1/3 times x to the 2/3. And so this, if I plug in 0, so f prime of 0 does not exist here because I'd be dividing by 0 here. And if you look at what the graph of this function looks like, f of x is x to the 1/3, right at 0, there's a vertical tangent line. The function becomes vertical for an instant at that point. And so in this case, the tangent line is vertical, so this limit, it doesn't approach a number, right? And so these are sort of the three main ways that a function can fail to be differentiable: if you have a discontinuity, if you have sort of a corner or a cusp, or if there's a vertical tangent line.